Welcome back to another video of Montes Mathematics. So for this video I'm going to be going over the functions of several variables, but now we're going to be dealing with domains. So let's just get into an introductory phase of this video and just understand what domain are we looking for and how do we actually obtain this domain. So here we have a hemisphere. Right now, for example purposes, I'm not going to give any technical names for the sphere. You should know the name if you have already done this topic on cylindrical and spherical coordinates and dealing with spheres. But let's suppose that this function, let's give it the name f of x, y. Okay, so this is a three-dimensional function. Whenever we are working with f of x, we are dealing with two-dimensional functions. But when we're dealing with three-dimensional functions, we're dealing with f of x and y simultaneously. Okay, and then obviously your output, so you'll be dealing with the x-axis and the y-axis simultaneously, while your outputs will be given on the z-axis, and that is why we have three axes for f of x and y. But now let's understand what is the topic of this video. We need to find domains of two variable functions, right? So let's do that. So what we are trying to say over here is we want to take this function, but we want to find out the domain, and the domain is actually represented by the shadow of this function. So what I mean by that, right? Look at this, right? So this whole function looks something like this. It's not like the neatest thing ever, but notice that the function looks something like that, right? But the shadow will now be what is at the bottom, meaning that whole region there, that light region right at the bottom, which lies on the xy plane, that will be our domain. So there, that will be our domain of f. Okay, and we need to find that. And in order to find it, we need to find the domain of the function that is given with x and y simultaneously. Now obviously, in order to fully understand this properly, we are going to go straight into examples, and then you'll actually see what I mean by this. So I've made the bold decision to before we go to the example, let's refresh our memories on the circle, because this is a very crucial step to most problems when you're dealing with finding domains, right? So let's say over here that you want to know x squared plus y squared equals 1. We know that is the equation of a circle, right? The equation of the circle is when we have x squared plus y squared, but now this is equal to the radius squared. But remember that the radius squared is just going to be 1 in this case here. And we know that if we take the square root of 1, we're just going to have 1. So that's just a unit circle, which is what we have here, okay? So here, it's just included exactly on the line of the circle. So the exact circle is the domain of that function. If we come, you'll understand it later. But for now, this is actually how we draw the circle where we have x squared plus y squared equals 1. The next one is x squared plus y squared is not equal to 1. Now this one looks more technical, obviously, because the last one we had it equal to the radius, right? Where the radius was included around here. Okay, so that's what we had. But over here, do you notice that it's not included exactly at where the radius will end, meaning at 1? Meaning we're going to write an asymptotic curve, which I did in dotted lines, where we will not include the circle, but we'll include everything around it. Because remember, if it's not this one, then it has to be everything around it. So inside and outside the circle, but not exactly on the circle, if that makes sense. For the next one, we have x squared plus y squared is greater or equal to 1. Now what this means is that it actually goes beyond the radius. Can you see that the circle equation goes beyond the radius, or it exists beyond the radius, meaning that it is every value that is higher than 1. So think about it, right? Once we reach that radius of 1 over here, do you notice that all the values would obviously be less than 1, will be between 0 and 1, which we can say this is a half. But we are focusing on the values that are greater or equal to 1, meaning we are going to focus on every other value that is outside of 1. And that is why this will be the domain in this case. Obviously the shaded region, which is referring to the domain of that circle, or the equation of the circle itself with the domain. Then the last one, which is x squared plus y squared, is less than or equal to 1. Do you notice, obviously now, with the last one, it was greater or equal to 1, meaning outside of the radius, which was 1. But this time, the circle is below 1, meaning the circle should exist, but now we're focusing on every value that is less than 1, obviously, in this case over here. So meaning that is why we shaded the inside of the circle. So this is important information for when we are actually sketching, because we are going to be sketching the domains of the functions as well for the two variable functions. Let's get straight into the first example. Okay, so for the first example, we have f of x and y is equal to 1 divided by x squared plus y squared, and we are asked to find the domain of f. Now, you can see that the equation of the circle is within, so it's somewhere here, right? But now we notice it's in the denominator. And remember, when we are trying to deal with something that has a denominator, we need to notice that the denominator must never be equal to 0, otherwise it's undefined. So what we need to notice is that the domain of this whole thing over here, right, the domain of the function is going to be equal to, well, there's not much to really work out here because we already see what the domain is going to be. The domain of the function is where x is the element of, actually no, just take note over here. We're working with two variables, right? The function f has two variables. So this is how we are going to notate it. It'll be x, y, element of the real number set in this third dimension, okay, or just x, y simultaneously, where we will have x squared plus y squared is not going to be equal to 0, okay, because we can't have that denominator being equal to 0. Right. Another way we could also have looked at it, right, is, or actually, you know what, let's do the sketch. What was the sketch going to look like now? Okay, so this is how the sketch is going to look like. So for these sketches, you're not actually expected to do the three-dimensional surface unless you are expected to do so. If they ask you to do it, then you should do it. But for now, when they ask you to sketch the domain, usually the domain would be the shadow of that function. And I'll actually get the function out for you once we're done with the sketching. So notice that x squared plus y squared cannot be equal to 0, right? Remember what we said earlier, when x squared plus y squared was not equal to 1, that just meant that it wasn't the circle, but it was everything around it, right? So when we say the radius is 0, we're just specifically talking about the fact that the circle is just on the origin, meaning it's just a point on the origin, but it's not equal to 0. So how do we indicate this? We indicate this with a excluded point, right? Remember that this is excluded. It's not a circle, it's just excluded. So, and then we just say over here, we shade the region around it, okay? So we shade the region around it, and then we will call that the domain of f. Just make sure that you're using the right color. And then obviously this one, you don't shade the inside because remember, it's supposed to be a point, but it is excluded on the origin over here, as it says. Okay, let me get the diagram of the surface so that you can actually see what's going on. Okay, so you can see here, here's the function that we have, which is 1 over x squared plus y squared. It looks like a funny function, and I just zoomed it out to 10 by 10, right, with the xy plane. Now notice that it goes all the way up, okay, because of that domain restriction. Remember that we said it was excluded, where x squared plus y squared equals is not equal to 0, right? But notice here that when it approaches the origin over here, it goes all the way infinitely up towards positive infinity for the z-axis, but it will never touch the point where x is either equal to 0 or y is equal to 0, when both of them are equal to 0, meaning the origin point. It will never intersect with the origin of the x and y. And another way you can look at it, which I also have next to it, is here, right? So we have this You can see by the shades and the glistering light and everything, you can see that it's going up. It's going towards us. If you think about the right-hand rule, you'll see that the thumb is pointing towards you. And the XY axis you can see here, meaning it's going to go infinitely up all the way to positive infinity within the Z axis, which is this dot over here. And then you'll see that it will never intersect with the origin of X and Y. So therefore, we have gotten it correct. There's a nice visual representation. Let's go to another example. Let's just keep trying to do more examples and understanding how we're really getting these domains. So here's another one. So you'll see that it looks almost exactly the same as the previous one, except instead of the plus sign, we have a minus sign. So meaning we're not dealing with a circle right now. We are now going to just deal with something else. But we'll see what we need to deal with. So let's get started. So from here, right, we know, okay, the numerator is just a constant value, so we don't need to look at that part. But now we need to look at the denominator. We know that x squared minus y squared, they cannot be equal to 0. So what I want to do for this one here is I want to introduce you to something of a notation that you can use. So since we don't have a circle and we can't use the x squared plus y squared not equal to 0 method, all we can look at is the fact that we know if we plug in x equals to 0, we're going to have 0, and if we also plug in y equals to 0 at the same time, that is now when we have the denominator to be equal to 0. Do you notice that? That's one of our conditions. So if x and y are equal to 0 at the same time, then therefore that means that we will have an asymptote around there. It will be excluded. So this is how we represent it. X and y within the coordinate cannot be equal to 0. So we're saying both x and y cannot be equal to 0. This is usually how we notate it. Okay, so this is not our domain yet. We're not done yet. So we have one of them. But what else can we take from this? What if we substitute something else, right? Do you notice that if we replace y with x, then therefore we are going to have x squared minus x squared. Do you see what I'm saying? Because then we're going to get the case like this. If y is equal to x, in this case, right? So I'm going to say here, if y is equal to x, then this implies to us that we are going to have f of x and x, because notice now I am changing the y to an x now, okay? And then this is now going to be equal to 1 divided by x squared minus, and then I'm just going to replace the x here, say x, but it's still squared, remember, because the y was also squared. And this will mean that we're going to have 1 minus, the x squares will cancel out, and we'll get 0. Notice that that's also how we can have an undefined denominator. So that's something that you need to look out for. And also, if we have the case where y is equal to negative x, then that implies to us that f of x, and we can say this is negative x over here, is equal to 1 over x squared minus, and then let's just put it in brackets here, we'll have negative x squared. Okay. And then notice that the square will just cancel out the negative, and therefore we are just once again left with 1 over 0. So therefore, this implies to us that once we have, so here's our different restrictions here. When x and y is equal to 0 at the same time, it'll be undefined. And if y is equal to x, then therefore it will also be undefined. And when y is equal to negative x, it will also be undefined. But do you notice that y equals x and y equals negative x are linear functions, meaning they're going to be straight line functions in our xy plane when we are drawing the domain. And then for this one over here, we're going to do the exact same thing that we did with the circle. We're just going to exclude the origin. So here, this is how it's actually going to look. So first of all, let's deal with the domain. So the domain of this implies to us that the domain of the function as a whole is going to be where x and y are an element of the real numbers on the third dimensional plane. And then here, or x, y simultaneously, and where we say x, y cannot be equal to 0, and then we can put in an and actually. So we can either say and like this, or you can say and, or you could say intersect. For this example, I'm just going to say and, okay, because it's easier for everyone to understand. And y cannot be equal to plus or minus x because of this. Okay, so because remember, when it is this, then it's going to be undefined. So that is why we're going to include that into our domain. So we can see it exists everywhere except for when it's on the origin and when it is a straight line for both the positive and negative gradient. So this will be the sketch now. Okay, so what are we restricting again? Here, let's do the asymptotes in red. So we are going to restrict the origin. So we're going to put a circle at the origin, okay, indicating we are not going to include that. And now, for this one over here, I'm going to do the straight lines, which is y equals x and y equals negative x. So I'm going to quickly just make it a dotted line quickly, an arrow, and then it's going to look something like this. So y equals positive x will look something like this, okay? And then y equals negative x will look something like this. Okay. So it'll look something like that. And then let's just write down our stuff over here, okay? So this is at 0. Oh, that is still a dashed line over there. So we're going to do a 0 over here. And then we are going to say y equals 2x. And then y equals negative x, okay? And then for our whole domain, let's do it in a different color. Let's do it in dark blue. Our domain will be everywhere except those lines and the origin. So let's just shade in the region around those lines and around the origin point. And then from here, that should be our domain. So this we can call our domain of f. Let's get a visual representation of a surface as well as the actual domain from the two-dimensional perspective. Okay, so from here we have this function, okay, which is 1 over x squared minus y squared. So this is what the function actually looks like. This is what the surface looks like. So notice that looks a little bit weird, but now you can see some gaps and whatever. But if we look at the two-dimensional perspective, so in the domain perspective, do you notice that the lines over here, this is the y equals x, this is the y equals negative x, and it's also excluded around the origin point. Obviously this is very zoomed in, so it's going to look like it's more than where xy cannot be equal to 0, but this is like an accurate representation of what it actually looks like. So you can see here, it looks very, very similar to what it would actually look like. Let's do one more example on this one, and then we can call it a day for this video. Okay, so for this one, we have f of xy is equal to the square root of x plus the natural logarithm of the absolute value of x squared plus y squared minus 9. Now we need to find the domain of f. So this one looks very intimidating, and I understand why. Because first of all, we have two functions, which is a square root function and a natural logarithm function. And then within the logarithm, we have an absolute value with a circle within it. That looks intense, doesn't it? Well, it's not. Let's break it down step by step and you'll actually see. It is a little intense, but it's not, because you can actually see there's a sequence to this. Let's start with the first function within here, which is the square root of x over here. So I would say, suppose that we have, suppose that g of x is equal to the square root of x, okay? Such that what we are going to have, I'm going to say such that, what is the domain of this going to be then, okay? Because remember, it's a function of one variable. So we'll say g of x is equal to the square root of x, such that we can say the domain of g is just going to be equal to where x is the element of the real numbers of the second dimension. Then we are going to have x has to be greater or equal to 0. Remember that square roots as an output will always be positive or equal to 0 when you plug in x values, okay? If you plug in a negative x value, it's going to become complex. When you plug in 0, it's going to be 0. When you plug in any positive value, it's going to stay as a positive value and exist. Okay, so that's the first one out of the way. And notice that you're going to take this function, which is square root of x, and then you're going to intersect it with the domain of this function at the end. So let's move on to the other one. So we are going to now suppose that h of x, okay, let's say h of x, and I can write that a little bit better. Suppose that h of x is equal to the natural log of the absolute value, I'm just going to write it like this, x squared plus y squared minus 9. Okay. Now where do we go from here? Do you see from the function within the natural logarithm, right, that this, for the output, we usually look at the output rather than when we have to find the actual domain first. For a natural logarithm in general, right, the natural logarithm, if anything is inside of the natural log, the output will always be either, I'm gonna think about outputs, the inputs, right? The inputs that you're given, it must not be a negative value, otherwise it's going to be undefined within a natural log. And the value must also not be 0, otherwise it's going to be undefined. If you see where I'm going with this one, okay? So therefore, this function must not be negative, and this function must not be 0, but it can be positive. But now we need to come to a sense that there's absolute values. So if there was no absolute values, you would absolutely say that we cannot have negatives. But in this case, because there's an absolute value, automatically, whatever negative thing you put in, it'll give you positive. So therefore, we only left with the fact that this thing inside cannot be equal to 0 for this whole thing to exist. If this function is not equal to 0, then therefore the whole ln function will exist. So that is what we are going to do. We are going to say here that the x squared plus y squared minus 9 cannot be equal to 9, okay? Sorry, 0, what the heck am I doing? Cannot be equal to 0, and this implies to us here that x squared plus y squared cannot be equal to 9. And do you notice that the radius of that 9 is just 3 squared, or just 3, sorry. So meaning the radius is equal to 3, okay? So let me make it less confusing and say that this implies to us that the radius is equal to 3. When we're drawing the circle within the domain, we will notice that the radius is going to be indeed 3. Okay, so from here, where are we going to get the final answer? Now remember, first of all, we know that for the square root of x, x must be greater or equal to 0. But for this one over here, we know that x squared plus y squared cannot be equal to 9 for the other function over here. So therefore, what this is going to imply to us is that the domain of f is just going to be where we have x and y is the element of the real numbers in the third dimension, second over there, where we will have x must be greater or equal to 0, and remember we're intersecting because it's a combination of functions, and we will have x squared plus y squared is not equal to 9. And then we can end off there with the domain. Now we must sketch this. So let me get the sketch ready for you. Okay, so from here we know that x can be greater or equal to 0, and we know that x squared plus y squared is not equal to 9. Obviously you can see what I mean by and, because in the same axis we are going to put both restrictions at the same time, so they must intersect with each other. So obviously with x greater or equal to 0, it can literally be this entire region over here, and I forgot to change that, but you know what I'm talking about. It can be in the entire region, which is around here, where x is positive. Okay, cool. So let me just label these axes, don't forget to do that. And then from here, let's first focus on this one. X squared plus y squared is not equal to 9. So notice that the radius is just going to be 3. So let me put a 3 over here, and let me put a negative 3 over here. Okay, such that what we're going to have, since it's not equal to 9, then therefore, we just call it, okay, let me first put also a 3 over here, so it just makes more sense. Okay, there we go. And then we're just going to say over here, and then over here. It's not the perfect circle, but you get the idea, okay? And remember, we know that the domain is not where x is negative, so therefore we can't place the stuff over there. We have to place the stuff over here. And since we know that x is greater or equal to 0, and x squared plus y squared is not equal to 9, then therefore we can verify that it will be this entire region outside of the circle, okay? So it looks something like this, and also within the circle. There was no restriction that was given within the circle. The only restriction that was given was the circle itself with the radius of 3, and also outside where x is positive or equal to 0, meaning this whole region over here. So therefore, this is your domain of f. Let's get the actual surface and see what's going on. Okay, so this is our function that we're dealing with, right? It's this function, okay? And then what you notice is that within the x-plane, right, the negative side of the xy plane, okay, so here where x is negative, it doesn't exist, but it starts exactly from where where it intersects the y-axis, and it goes all the way up with the z-axis and down along the z-axis, and continues along the positive x-axis. That was a lot of stuff that I just said right now, but if you just listen to it slowly, you would actually get what I said. So notice this is what the shape looks like, and you can see the restrictions. You can see the cutoff over here, that it only exists in the positive x side and the negative and positive y. Okay, and then in the two-dimensional aspect, you can see here, this is what we had, right? It doesn't exist where x is negative, the whole region over here, and it also doesn't exist on the circle where the radius is equal to 3. And it exists everywhere around that, past the y-axis. So you can see, it looks something like this. You can see it excludes the circle, and it also excludes the region on the left, and then it includes everything else. And that is how you can actually verify all of this stuff. So this is an introduction to advanced calculus, right? And that was the last question. This is an introduction to advanced calculus. It looks intense, but I would recommend that you go and graph these functions yourself, and then try and get used to them, see the patterns and everything, verify your answers not with AI, but with Desmos, and try and understand where you went wrong or where can you go do better. So that was it for the functions of several variables with domains.